We're going live, guys. Stand by. If I can get like a 3, 2, 1 kind of thing. Thank you, Colby. We're there? We're live? Oh my God, we're live. Okay, guys, it's happening. Okay, so yeah, thanks for everybody coming. This is we're with Ogden Avalanche. I think most people probably know about us or you wouldn't be here. But yeah, we're a nonprofit ran in the Ogden area for education and outreach. Just trying to enlighten more minds about snowpack and or avalanche related things. Mine's weather tonight. So this is a first, weather. We'll see how this goes. Not my strong point, but so this is a first night of a 5-week speaker series. So it's kind of like a progressional thing. So if you're into it and you want to continue to learn, it's obviously tonight. So you made it tonight, and then there's 4 more every Thursday for the next 4 more weeks after tonight, which goes into snowpack, terrain, avalanche accidents, and then rescue. And if you've never seen Brandon Everett talk about rescue, you better get here. It's pretty good. So, awesome. So, yeah, we're going to jump into weather right now. Maybe that's the code word. Oh, that's why everybody's drinking. There's a code word, weather. Yes, this is great. You guys are going to be so drunk by the time I get 2 slides in, it won't matter what I say. This is awesome. Okay, so my name's Nichole. I work with Ogden Avalanche, have for a few years. Some years I knew about it and some years I didn't. But the last couple I've been pretty involved in it. And then also snow safety director at Powder Mountain. So thank you. I deal with a lot of weather. This is great. So let's jump into this. First off, I just want to give you a warning and or a disclaimer. I am not a meteorologist. I'm an avalanche forecaster. So if you have questions about snowpack or avalanches anytime tonight or during the rest of the 4-week sessions, I'm kind of your girl on that. I got roped into the weather part. So I'll say it again, weather is very complex and we're going to try to keep it really, really simple tonight, right? It's like I was trying to write this presentation and I would like define like a concept and then I would realize I would have to define words in the definition of the last concept in order for you to even understand the definition. So it gets a little heady. So try not to like slap me across the face with really hard questions. And once again, there's going to be questions that I probably can't answer. Maybe we can email them to like a meteorologist or something, but I'm going to do like my very, very best to help you out and teach you stuff. So talking points today, we're going to go over, it's a little dark, sorry. Meteorology, basic review of just terms that we use, if you will. Lifting mechanisms, mountain topography, orographics, which is something everybody should be super into, and you'll understand it after I teach you about it. This is why sometimes we get a lot of snow and sometimes we don't, even with systems that look to be favorable in our direction. Convergence zones and favorable flows for our area. And I love to keep this Ogden oriented, but I got to say the Central Wasatch has like a really cool thing that happens. And so I will talk about them just like a teeny bit. Localized orographics, we'll go into like some Google Earth stuff. I have some cool stuff going on there. And then blocking patterns, which we're currently in. And then just a few tools for you guys. I have a few book recommendations and or websites. You could like take a snap of the screen or whatnot, or I can email them to you or whatever you want. So meteorology, it's the study of Earth's atmosphere and the variations in temperature and moisture patterns that produce different weather conditions. That's kind of the definition. But in a nutshell, what we need is lifted air. We need air to cool. We need it to condense to a dew point, clouds form, and then we get snow. That's kind of like the basics of the system, right? There's a lot of stuff going on, but all of these components here need to happen, and then you get some sort of precip, right? And in the winter, hopefully it's snow, even though it seems to be a little bit more rain these days. So just a basic review of a few words. An air mass. This is characterized by relative temperature and humidity. They can be wet and or dry, right? So it's all relative. It doesn't mean that it has to be wet or has to be dry. They can be warm or cold, wet and dry. And then the thing that does us good, or what we like to see, is when different air masses come together, right? That's when we start getting weather, basically. So when warm and cold, relatively speaking, clash, that's when we start seeing weather. Yeah, why aren't you guys drinking? Weather. I'm just kidding. So these are the different air masses right here. These kind of, generally speaking, sit in these areas. Obviously, this is all kind of a fluid situation going on. But the maritime, the continental, polar up on the top there, and then the tropical down on the bottom, you're going to see these air masses correlate with the jet stream as well. And we'll go over jet streams here in just a little bit. Storm systems. This is where a different air mass that we just covered meet or collide and the storm develops, basically. This is known as cyclogenesis, and a cyclone is simply a low pressure. That's all it is. The bigger the difference in the air mass, the stronger a storm's going to be. So that's what we like to see is like frontal passages that are very, very extreme are going to give us a lot more precip, if you will. Or winds, maybe, I don't know. But this one gets a little heady, but this has like a huge play in what I'm talking about, which is weather. I don't want to say it a whole bunch. Now I feel like I'm just like killing it. I'm ruining the word. Large scale movement of air together correlated with the ocean circulation, right? So this means that thermal energy can be redistributed on the Earth's surface. I know this is like super sciencey, but that's what it is. The circulation varies from year to year, but relatively speaking, on like a large scale thing, everything stays the same. That's why we get snow typically from October to April, and then it gets warm through the rest of the year, right? So relatively speaking, these things stay the same, even though we have, for us, good years if you're a skier and or poor years, but for the most part, it stays the same. Oh, the Coriolis effect. Ooh, this one's heady. This is basic. I'm not even going to really go off the total definition, but based off like the way the Earth is spinning, everything deflects like a certain way, right? That's how weather comes in. That's how our patterns and our storm systems come in. And that's all based off the Coriolis effect. Okay, I'm not going to get crazy, but I do have a couple little diagrams that probably will confuse you more. So objects deflect to the right in the northern hemisphere, which is what we deal with, and then to the left in the southern hemisphere, based off the Earth's rotation. No questions, right? Great. Let's just skip that part. Let's just move on to things that I know a little bit more about. Yeah. Actually, I'm just omitting questions in certain sections. I'm not allowing questions in certain sections. Oh, jet stream. This one's like a pretty popular one. This is one you should follow. This is the full driver of all our storms. This one's an important one. So the area of fastest wind speeds in the atmosphere. Does anyone know what the jet stream is? How high it is? No, not 700 millibars. 30,000. That's what it is. That's your jet stream winds. That's where you should always be looking to see really what's coming our way. So that's the 300 to 250 millibar range. 330, it's pretty easy that one's pretty easy. 700 millibars is 10,000 feet. That's our ridgetop line, or winds. Yeah, so the jet stream, that's a really, really important one. That's going to tell you all the driving forces going on into your area. You should always be looking at jet stream winds. It's also a dividing line between the coolest and warmest air in the atmosphere. So that's why that thing shifts back and forth, right? So there's going to always be cool air probably on the northerly side of it, and generally speaking, and warmer air on the southerly side of it. There's two types of jet streams that we deal with. One is a polar jet, and that correlates with those air masses that I just showed. It moves generally westerly in direction in mid-latitudes. That's where we find that one. Get your food. The subtropical jet, this is the one that we like to see with moisture, right? This is our big moisture one. It lies above regions of the subtropical high pressures, and then it travels in the lower latitudes or slightly higher elevations. So if you ever look at, like, I think we'll be able to see it on a map I have, but the polar jet is always going to be higher up, and then you'll see the subtropical jet coming like down in below California or something. When those two decide to like come together, what do you know what we get? What was the term in, like, when was the big snowfall? 1617 or 1617? A squall? Ooh, there it is, an atmospheric river. That's what happens when those jets come together. Yeah, table in the back, the Snow Basin / Powder Mountain table, just getting it done. Yeah, when those two jets come together, that's an atmospheric river typically. That's when we get good cold air and lots of moisture. That's what we like to see. So right here, this is just a very basic diagram. This correlates with those air mass pictures that I showed earlier. The polar jet sitting on top and the subtropical jet just sitting down below. Pressures. So high and low pressures are the two types of pressures that we have. High pressures, ridging, which is kind of what we've been in for the last little bit. We have a little cold dry front coming through with no moisture, but these ones are clockwise circulation. That's how you can recognize what a high pressure is. Shane, over here. Anyone else? What else you got? Well, we're messing with you tonight, Shane. So high pressure, that's ridging, clockwise circulation, diverging flows, so away from each other, and sinking motions. Does that make sense? Low pressures are known as troughs, and I'm going to show you these. They're counterclockwise, they're converging, and they're rising air, which is good. That's what we need, because what do we need? We need lift, right? And lift condenses moisture and makes clouds and makes precip. So low pressures are good for us. How I remember the high pressure thing too is I just think, so high pressure spin to the right clockwise. If you take like a screwdriver and put a screw into a piece of wood, you turn it to the right and you push down. So that's kind of how I've always remembered the difference between high and low pressures. I learned that in a forecasting class. So here's just a picture of these. The high pressures and low pressures, and showing kind of what they do. A high pressure is down and the winds push out. Winds come in and lift for the low pressure. And then I have this really cool thing, but I did talk about how nothing works out in my favor to Colby just a minute ago. And we were under a really cool little borderline high amplitude ridge. So we're right here. See that? That's the Great Salt Lake. And now this thing used to be this green part that's spinning clockwise, right? Used to be kind of up on here, but we have a low, which is right here. Can you see my mouse? Yeah, okay, cool. We have a low that's coming in right here. So we used to have a higher amplitude ridge. That's why we were seeing so many beautiful sunny days. But right here, this is a trough and a low. So it kind of, that wasn't a joke or a low. Oh, a low. Okay. What's high? Let's find a high. Oh, okay. Oh, okay. So this is a really cool tool too, where it shows like, this is now though, right? So if you ever want to go to Japan, this is why they do really good. And John Fisher just came in. They get very like progressional. They don't have a lot of mess with their jet stream because they don't deal with like ocean currents, where we get these like ocean currents that warm everything up, and then with these big high pressures right here that like to build either a high amplitude ridge or a dirty ridge, and it kind of messes us up. I can share this link. This is like a really, really cool thing interactive thing to see these pressures and the jet stream winds. Let me exit out of here real fast. Okay, fronts. So we have a few different kinds of fronts: warm, cold, stationary, and occluded. Once again, this gets a little bit heady, But warm fronts are slower moving. They're going to see like stratus type clouds, so like the long wispy stuff. And then if we get warm, you're going to see long and steady precip because they're slower moving, right? Cold fronts are faster moving, and then we get the big cumulus clouds, the big poofy ones, right? And this brief and heavy precip is basically how this is. Whoops. So here's just a picture of different. This is a cold front versus a warm front. You don't necessarily need to like know a ton of this. The shape, that's like a little bit kind of heady, but it shows how aggressive a cold front is compared to a warm front, basically. So a cold front's going to come in fast and hard and bash into warm fronts. That's basically kind of how that happens. But those are the difference between them. If you ever look on a weather map, the cold fronts are the blue. I like forgot already. The cold fronts are the blue little triangles, and the warm fronts are the little, I don't know what those are, little mounds, red little mounds, I guess. So that's kind of how you can tell the fronts between each other. Stationary front. It just is what it is, what it says. A stationary front forms when a cold front or a warm front stops moving. So this happens when like we don't have an air mass that can overpower another air mass. So they just kind of bash into each other, and they're just kind of dealing with this equal power struggle, basically, and they can't move each other out. Occluded fronts. This initiates when a cold front overtakes a warm front. And so you can see right here where the cold front is starting to fall over the top of this. This is the occluded area. Occluded areas usually mean really intense precip, right? Oh, let's see. Okay, I think that's it on fronts. Lifting mechanisms. This one's a real big one. This is one you want to like pay attention to if you ever get into the world of forecasting or looking at models or anything like that. Lifting can help us a ton, and it's what we need, especially with like the big Wasatch Front to get up over the top of. So there's cyclonic. That's from convergence around a surface low pressure. So we have like a low right on the ground, basically, like in the town of Ogden, let's say, and it's going to lift air up over the mountains, basically. That's what that one's doing. A frontal lift, that's from the dynamics associated with a frontal passage. So you'll see like these walls of clouds moving across the Great Basin, really, really intense winds and a lot of stuff going on that. That'll push stuff over the Wasatch Front as well. Orographic, that's a big one for us. We're going to go over that in a flow against like our mountains and our topography. I hate to say it, the central Wasatch gets more snow than we do. It's purely orographic based, especially smaller storms, right? So big storms can encompass like a lot of area, but smaller storms really need like a lot of mountains and topography and things like that to get themselves generated to higher precip levels. And then there's convective. This is generated by surface heating or instability. This is a little bit more of a thing that happens in spring and summer during thunderstorms, but with like the warmer temps that we've been seeing and stuff like that, we've already had thunderstorms and lightning holds during the winter already. So convective is becoming a little bit more popular around this area. So mountain topography, rough terrain causes storms to lose some energy due to friction in the surface. And when I start talking about mountain topography and or orographics, I spend my whole summers on a river. And so that's like a really good correlation for me when I start looking at wind and or air moving through something. Think of like a river, right? When we're talking about all this stuff. So when there's a pinch point and then it opens back up, water speeds up, right? When it has to go around things, stuff like it's going to make sense here in a second. But if you can't picture the way this works, water always seems to help a lot. So the rougher the terrain, it can cause friction and slow a storm down. At the same time, just like everything isn't black and white, rough terrain can cause areas of turbulence. So it can cause areas of lift and increase intensities in storms. Terrain highly influences direction of storm tracks, especially when you start talking about big mountains. Small systems tend to feel and interact with terrain below. So you'll see them like migrate with terrain. They'll get trapped in things and follow the path of least resistance. Large systems tend to not have to worry about this, right? They're so big they can encompass everything. And that's when the orographics don't matter quite as much. And then the position of that surface low is a really, really big deal. I didn't do like a diagram of this, but if you can have a surface low in your favor, what's going to happen is the low is going to spin into the mountains and lift. But if you're on like the other side of the mountains and you get the spin the other way, there's no lift. Does that make sense? So like if I'm spinning and I run into this computer, I'm going to raise up. But if my spin is on this side and I run into something, there's nothing here. So I'm just going to keep going. So over here is not going to get any snow, but over here is going to get tons of snow. So the position of a surface low is really, really important. Okay, so orograph and like really understand your terrain. And when you're picking like your next location to move to, you should look at like locations if you're moving for snow, I guess is what I should say. So understand clouds, which we already went over, and precip, where no cloud would be occurring or precip are occurring in adjacent valleys. I mean, it's as simple as 10 inches over on this side of the room and 0 inches over here. That's how dramatic it can be with lift. So orographic and flow directions, perpendicular are the best. That's the best you can get. So running straight into something is the best you can get. Oblique is pretty good, right? So if I run straight into this computer, I'm going to tip it over. That's as good as it can get. If I come and hit it kind of at the side, I'll show you another one that's really good for us for Powder Mountain here in a minute. But precip is enhanced in a very concentrated area, so it's not going to be like widespread. It's going to be wherever it blows up on, basically. And then combined with that good orographic wind, once again, can result in really good dumps. Lee side convergence. This is limited to lone peaks, so like single peaks in somewhere. I would say that the Tetons could probably fall into this range. What's going to happen is flows are going to come and hit a peak, and then they're going to go around them, and where they rejoin again is where you're going to get a whole bunch of snow, right? So big, long peaks is where you're going to see that kind of stuff. And the snow is going to be on this side, right here. This is not going to get hardly any snow, and this isn't going to get any snow. Upslope convergence. So this is when winds are coming up from all directions off the top of something, and all the snow is on the top of it. Pretty simple. Not that complicated. Displaced convergence. So this is one that like we probably see quite a bit when you have a parallel hit to something. So produced where air being lifted on leeward slopes, so the winds coming up on leeward slopes meets the upper like flows aloft, basically. So I don't know that it's necessarily jet stream winds, but maybe like the 500 millibars, so the 18,000 foot areas where those lower winds are gonna meet up with those upper winds. And then snow, so this is strong wind right here. This wind hits this wind. Does that make sense? And creates a whole bunch of snow on this side of the mountain. We see a lot of displaced in our areas with that big wall of the Wasatch Front here. So this is, I'm gonna go into a little bit of local orographics here. And I kind of showed you the central Wasatch and why they do so good. And I mind you, I'm very, very familiar with Powder Mountain's flows. I'm fairly familiar with Snow Basin's flows. And I have no clue where Corey is, but he could probably correct me and or help me if needed as well. Let me get myself oriented here. Oops. Ooh, I might not. Oh, there we go. Weather. Oh my gosh, so great. This is just so great. Oh, so awesome. Okay, let me orient myself. I apologize. Let's go this way. Okay, so the little dot here is Powder Mountain. That's kind of like right on our main parking lot here. We do really well on southwesterly flows, but I also think we do well on southwesterly flows because we get a lot of southwesterly flows, right? But the reason we do well is because we have like a decent lifting mechanism right here. So if we can get either a flow from right here or a zonal flow, we do well on westerlies as well. It bumps up over Ben Lomond and Willard Peak and, oh my gosh, what's the other little peak? Lewis Peak, yes. Thank you. It can get up over there and get to us. The flow that we do the best on, does anyone know, minus the people that work for me, the flow we do the best on? Okay, well, I just said that. Brittany, you were doing so well. I just talked about southwest flows. We do well on southwest flows, really well on southwest flows, but we get a lot of southwest flows. But if I had to compare the numbers, so southwest might be out, right? You only have a couple other options. No, we suck at northwest. We're horrible at northwest. Does anyone know why we're horrible at northwest? You can't answer any of the questions. There's these two gigantic mountains to the northwest of Powder Mountain. So Ben Lomond and Willer Peak block us from any snow. Ben Lomond will get hammered and we'll get nothing. I mean, hammered and we'll get nothing. It can't, most storms, unless the storm is so big, can't get to us on a northwest flow. Okay, next. No, there's not that many other directions. No, guys, come on. North. Oh my God, we do so well on north. Cache Valley Effect. So if you look right here to the due north of us, there's a really good convergence zone right here, right? So we have like a nice convexity. We get a whole bunch of channeling right here. North is Powder Mountain's best flow. We just don't get a lot of north flows in this area. Snow Basin, they do really well on northwest and on southwest and on west. That's about, north is about the only storm that we can beat them out of. But whoa. What's that? Oh, no, don't say that thing. They all love each other and appreciate each other. Yeah, so Snow Basin, right over in here, right? This is why they do really well on zonal flows. They're on the front and southwest and northwest. They don't have anything blocking them. So that's why when a northwest flows comes in and marketing's mad at me because we only got 2 inches and Snow Basin got 14 and they say I'm lying and they don't understand. Where is the marketing team? They're supposed to be here so they understood these things. Ugh. They're probably on social media right now talking about the cold front coming in and how we're not going to get some snow or something. Too bad they're not here. Love those guys. So I'll roll down here one more time just into the Central Wasatch and went over. But the big hatcher's mitt is why they do so well on a lot of stuff. And then the really well for the wind side of it too, right? So a zonal or a southwesterly flow goes straight up that canyon. Yeah. Is there questions on like orographics or flows, or this is the topic you can ask questions about? All right, cool. I would have been a ski resort builder. I would on my orographic. So missed. But if they did, it was good. Ooh, like that's a good question. Like percentage wise, I can't even tell you. But that's a good answer. I don't know. There's nothing wrong with admitting that you don't know something. But no, but in all honesty, it's we don't get a ton of due north flows. It just doesn't happen because our weather doesn't come straight out of the north. It comes weather. Yes, it moves. All the flows are going to move from west to east, right? So you need like some sort of a high pressure to bump us north, or you need like a low pressure to come down and shift that as well. We don't get them a ton, predominantly southwesterlies. I apologize, coming from the north. Yeah, so if I say southwesterly flow, it's coming from the southwest. Westerly flows or zonal flows are coming. Oh, I just took the Google Earth down. Does that make sense though? California from Utah is a westerly flow. Coming from. North flows from what? Yes, sure. Flows from all the directions would be nice. I appreciate the passion. Chuck is intense right now about the flows. Oh my gosh, it's great. I love it. All flow. Let's see here. Rex block. There's the so it's when the high pressure gets located on the polar side, so the northerly side of a low pressure, and no weather can get into. I mean, this can be relative to anywhere, right? I just took pictures of I just got these for the United States. But what you'll see is weather going up and over everything. So nothing gets weather. It's cold here, but you don't get a ton of weather. But then this is like intense, like extremely intense, like flooding and stuff like that. So that's what you'll see out of a Rex block. And it just makes like a big block, basically, like a big square block. Okay, the omega. This one's kind of cool, omega. And this is a combination of two cutoff lows. I'm not going to go into what a cutoff low is, but a combination of two cutoff lows with a high pressure sandwiched in the middle of them. We had a few omega blocking patterns last season. We got plagued by the dirty ridge, if you will, as well. But yeah, the omega, you can see the lows come down and then a big high pressure and then a big trough again. Split flow. Anybody that went to high school in Utah, well, I'm graduated in 2001, so around 2004 maybe, probably remembers split flow. It was like the term of everything. Everybody except for Utah got storm. We were in a constant split flow. So I couldn't find one of the easy diagrams. So this is off of a weather model, but a high pressure gets stuck right in here and the flows look amazing. You're like, damn, look what's headed for us. We got an atmospheric river. And then it hits this thing and splits and you are just high and dry. Split flows are horrible. Yeah, bad split flow. Boo. Boo on all blocking patterns, right? It's nice to, yeah, okay, thank you. Blocks are nice for snow safety people, like every 3 days. But we don't want them in between that. We want kind of like 4 days of snow and 3 days of blocking so we can get some rest and some sleep. Okay, cool. I'm like pretty much done. So these are like a few tools for you. If someone wants me to go through these, I can. It's just I didn't want to go through weather models. I talked to Corey on the phone, decided that was a little scary. Deep, dark hole that I didn't want to get people into. But these are some really good books. So if you want to take a snip of these, Jim Steenberg. He works for the U of U's. Ask him to email. He'll probably kill me, but he takes emails and stuff like that. He also writes yeah, that's a good blog post. That's a good one. You should look at that one. He does a really good forecast. He does really good recaps. So yeah, local guy. Mountain weather, backcountry forecasting for hikers and campers. I don't know this guy, this Jeff Renner, but it's a good book. I own the book, and it really simplifies everything. I pulled a lot of stuff out of there. So if you are into this, and it also goes into not just like skiing and snowboarding and stuff like that. So you could relate these things to like summer activities and gain stuff off of it too. The mountainweather.com, that's from Jim Woodmansey. He's up in Jackson Hole. So he's a forecaster up there, and he's who I took a bunch of my mountain weather forecasting courses through. We're almost done, so get it in while you can. This can be a deep dark hole right here, but it's a really cool website. He's got things pertaining just to mountain weather states. So you can go into like Utah, Colorado, Wyoming, Montana, all that stuff. He has things relative to just those states. And then he also has like a ton of global stuff as well. And you can just like click and play for days on all that kind of stuff. And then this is something that has a lot of big words in it, and we read this every single morning. This is just a website to the NWS's forecast discussion. I don't typically use a lot of NWS stuff because there's a lot of variance in their stuff, but the forecast discussion is really good. They do a short term, so like what's happening, today and tomorrow, and they do a long-term forecast for what's happening for the next like 4 to 5 days, I would say. And they're really, really good at updating it as things change. So if you don't have the bandwidth to go here and go through like weather models and understand all the winds and the moisture and all this kind of stuff, the lift and the vertical velocity and all these things I didn't even talk about, this is a really, really good spot for you to look at stuff in the morning. It'll give you a good idea of what's going to happen in your mountain areas. Is there any questions? Yes, what's up? Yeah, totally. Yeah, that is a good question. That one. Oh, I have to repeat it? Okay, can you, oh yeah, we're live. Different systems that come from different directions, do they produce different types and or kinds of snowfall? And ultimately more or less danger in the avalanche world? Okay, now you're stepping into my world. Okay. Yeah. Yeah, let's close this and talk about avalanches for a second. So, yes, no, that's a really good question. And yes, they do. So northerly flows are typically going to be cold, low density snow because they don't pull as much from a tropical jet. But southwesterly and or westerly storms are typically going to be warmer. So they're going to be higher density. So we talk about this all the time. I don't want to go down a rabbit hole, but we talk about water versus snow all the time. And if you're like a snow safety person, you are worried about water weight. We don't care about snow. Marketing cares about inches of snow. We care about inches of water. So a north flow is going to, a north flow is going to give you the beautiful, like 7% Champaign, Utah density snow that we like to see, right? A southwesterly flow is going to give you probably more. I think we average 9.98% density at Powder is what our percent is, which is still great snow, but it's nothing like a 7% storm, right? So yes, they do bring, and then as it comes to danger, that's like not my topic for today. You'll learn more about that tomorrow, but I'm sorry, next week. Don't come tomorrow. We're not here. I mean, you could come and enjoy some beers at B Street and get the deep slab pale ale and help us out a little bit. No, but as far as danger, that's like that kind of goes down like a different rabbit hole. So more water weight you would think would equate to more danger though, right? So, but I don't know if I should answer this question. Okay, so let's say we have like a really cold storm, right? Out of the north, and then temperature's warm, and so we get a whole bunch of warm snow on top of it. So now we have strong over the top of weak. So yes, that would create a problem, right? Because the weak is going to fail, and that's where we get avalanches. So avalanches are all strong over weak. It's all relative. It doesn't matter what it is. Strong over weak causes an avalanche. And then a trigger, right? And that's either water weight, a human, a whatever it may be. But if we get a warm storm and then it cools throughout the day, we could have strong snow on the bottom and relatively, you could say weaker snow, but we wouldn't call that weak snow because nothing's on top of it yet. So that could create maybe not as catastrophic and or as big of avalanches, but you can still get avalanches in that dry snow. So you can have dry looses, right, versus slab style avalanches. So it's not really that like a weather pattern increases danger. It's how these like storms and patterns come together that will either increase or, and no weather pattern's ever going to decrease danger. Time is the only thing that can decrease danger. So for it to come back to its equilibrium and its constant, but like north doesn't like scare me and be like, oh, we're going to have a lot of danger. Southwest doesn't scare me and say we're going to have a lot of danger. It's all what it falls on top of and how the storm comes in. That's how our danger is going to increase. Does that make sense? Okay. Well, no, not in the book. Not in the book world. Yeah. Maybe it'll make like Oprah's book club. Or I could get on like Ellen or something. Yeah, that would be sick, right? I know. That was a good question though, but it's just a little more complex than like north is scary, southwest isn't, or yeah, there's a lot more to snowpack than just that, or danger. Is there any other questions? Yes, Chuck. Oh my gosh. We're not a center. That will be a question for Corey Davis. And we have a guest appearance by Corey Davis tonight.
I have a really simple answer. I don't know how to do that.
All right, Chuck, we're going to hire you as an intern, and we're going to get that all set up tonight. Yeah.